In this part we want to analyze the running time of the Splay function and prove the so-called access lemma. The access lemma is the key lemma to prove all those properties of the Splay trees. So what do we want to do? We want to look at some rotations. That's all we do in the Splay trees. And we have the sum of weights for our key that we query or that we splay upwards before the rotation. And we have the sum of weights afterwards. We will prove this in the general setting with general w's and not just one, because we will need some different functions later. We want to prove first, if we do a single rotation, then the potential increases by at most 3 times the change of the logarithms of the sum of weights of this key. So in a single rotation, the potential always goes up if you look at this. The x moves up, so the sum of weights here will always be larger than that one. So after we do a single rotation, we will always have an increase in potential, which is not good, but which will be offset by the double rotations later. How do we prove this? Let's say we do a right rotation. The left rotation works exactly the same, so we only do this one. So we have this situation here, we have our x, its parent y, and we want to rotate it to this part. Now, what changes in the sum of log potential? If we look at all those vertices in the yellow tree, for them, nothing changes. Every vertex here will still have the same sum of weights. The same from the orange to the orange and from the red to the red. So for none of these vertices anything changes. Also for all the other vertices that are not in the picture, like the parent of x here or of y here, nothing changes. The only 2 nodes where the sum of weights changes are x and y. So we only have to figure out how much does it change here. So the new potential that we will have after this rotation is the new sum of weights of x and y minus the old sum of weights, of course the logarithm of all of them. So how can we figure out how much this is? Well, for y the sum of weights definitely goes down from here to here, because it still has the orange and red, but it loses the x and the yellow. So this part here is always smaller than 0, so we can just remove it and say the potential change is at most the logarithm of the new sum of weights of x minus the logarithm of the old sum of weights of x. And this is almost what we want. And since we know that the sum of weights of x always increases, we can just take this times 3 and then we get our formula. So actually we show something stronger, but for the analysis later it will be easier if we have the number 3 here, even though it only makes things worse, but it makes the whole calculation much easier later. So for the single rotation we have proven this. And now we want to move on to the double rotation. And in a double rotation we have to prove something better. If we again only prove this, then we will have that whatever rotation we do, things always go up. That's not so good. But in the double rotation, we also have a -2 here. And that will be a key part later. So we want to prove that after a double rotation, we have this increase. And now it might even go down. So depending on how much the sum of weights in x increases, this here could be smaller than a 2. I mean, it's still something positive, but it can be smaller than a 2. And then the potential could go down by this double rotation, and the whole thing becomes more balanced. That's also something that we saw earlier. I mean, if we just do a single rotation, then, well, we don't know, does it go up, does it go down? But if we do this double rotation, then often those smaller subtrees become more balanced. So it does help indeed. There are 4 types of double rotations. 2 of them are symmetric. So we will start with the right-right rotation. So we have the following rotation. The x is here. Then we have the path to parents y and z. And we want to go here. And just like in the single rotation, what we have to analyze is how do the sum of weights change only in these 3 nodes. For all these other subtrees and whatever is up there, nothing changes. And this is a bit more involved than what we did before, but we can still figure something out. So if we look at our vertex x here, that contains everything. And in the beginning, number z contained everything. So those have exactly the same sum of weights. So we can just remove this part and this part, they offset each other. And now we will do 2 very small adjustments that don't help so much on first sight, that will make it possible for us to remove all this stuff. So first we look at the x here and the y here. The sum of weights of the x is clearly smaller, so we can replace the y here by an x, and then we removed one of the terms. And then we look at the y and the x on the right side. The y clearly has a smaller sum of weights, so we can just again remove the y and replace it by an x. Okay. And now comes the key part. Can you find something that we can do now to get from here to here? We want to look at this subtree here, the green part, which contains x and the yellow and the orange tree. That is the green part here. Then we have the purple part here, contains z, red and pink. That is the purple part here. So what we know is that this green part plus this purple part is at most this gray part. And this is equal to this. So we have the sum of weights of x, which is the green, plus the new sum of weights of z, which is here, the purple, is at most the new sum of weights of x. Because if we look at the sum of the logs of these two, we can use a standard logarithmic function. This is just log s of x times s plus of z. And then we can use the arithmetic mean, geometric mean, that this tells us from here, this product of these two is at most the gray divided by 2 squared. This is just the arithmetic mean, geometric mean lemma. If you have 2 numbers whose sum is less than equal to a third one, then the product is at most the third number by 2 squared. And then we again use the standard logarithmic functions. We can pull the 2 to the front here. The divided by 2 becomes a minus 2, so we get this. So if we pick log s of x and log s plus of z, we can replace it by this. If we apply it here, well, we have minus 2 log s of x, so that becomes minus 3. This one gets removed, and this here gets added. So we have 3 times the new sum of weights of x, minus 3 times the old sum of weights of x, minus the 2, which is exactly what we wanted. And exactly the same way we can also do it for the left-left rotation. There's one rotation left that we need, which is the right-left. So we have this situation, the x is here, then we have y and z, and we want to move x to the top and things to become more balanced. So what happens now? We again have to look at the potential change, sum up the logs of the sum of weights of these, and we again do something very simple in the beginning. We have the new sum of weights of x is the same as the old one of z, so those of z here, we only have 4 terms left. We have again that the sum of weights of x is less or equal than the sum of weights of y, so we can replace this by an x. But now how do we continue? Now we have a slightly different situation than before. Can you find something? We'll do something again similar. So we look at this green tree here of the y, which is this part here. And we look at the purple part here, which is this part here. Now we have the same as before. This green plus this purple is at most this gray. So we again can sum up the logs, and we can use the exactly same method, arithmetic mean, geometric mean, and we get that the sum of these logs is at most 2 times the log of the gray minus 2. And we plug it in here, and then we get even better 2 times log of the new sum of weights of x minus 2 times the old one. And since again we clearly see that the sum of weights goes up from here to here, we can just make this a 3 to get our lemma. And the same of course holds for the left-right rotation, as that is symmetric. So we have the following lemma. After a single rotation, the potential increases by this much, and after a double rotation by this much. And that we want to use to prove the axis lemma. And the axis lemma, that's the key part of everything. That tells us the amortized cost of the Splay function is 1 plus 3 log the capital W divided by the weight of the node. So in our example that we had where all the nodes have weight 1, this is just 1 plus 3 log n. So the amortized cost of Splay becomes log n if we just choose the weights as 1 for everything. And this is already a big step. So how do we prove this? So we assume that we have k double rotations and 1 single rotation. You can also easily prove it the same way if we have only double rotations, but since the single rotation is the bad guy, we will just do the harder case and then the easier case follows. So what happens? We have k double rotations, so the potential increases by k times this, and 1 single, so again by this. So let's say that after I single or double rotations, Si of x is the new sum of weights in x. Then the potential at the end will be for every step, for the first k double rotations, we have exactly this function, plus for the last step, we have this function. And now the key is we have all these differences. We go from S1 to S2, then from S2 to S3, from S3 to S4. That means that all those cancel out. So the number 2, it will be once here, and it will be once here. So that cancels out. The number 3 will be once here and once here. That cancels out. The only that do not cancel out is the very first, that's once here, the S0, and the very last, the sk plus 1, that is only once here positive. So we only need these two. So we get 3 times the log of the last minus the log of the first minus 2k. The 2k comes from here. And this is the root at the very end. X will be in the root. So we know exactly what this here is. This is our capital W. And in the beginning, what was the sum of weights of x? Well, if we want to figure out how large this is at most, then we need some lower bound on this. And this is at least the weight of x, because x of course is in the subtree of x. So we replace this by w of x, and then we use the logarithm rules here to get 3 log w divided by w of x minus 2k. So this is the potential change after all these rotations. And now to get the amortized cost, we need the potential increase plus the real cost. The real cost was k double rotations and 1 single rotation, so 2k plus 1 rotations in total. And then if we add this here, then we just get 1 plus 3 times the log of that part, which gives us the axis lemma. And in the next part, I will show you how this axis lemma gives us all those properties, or some of those properties. I will not show all because we don't have that much time for the Splay trees.